Data representation. This module describes about the representation of data while storing and processing it in a computer system. Modern computers store and process information represented as two-valued signals. These binary digits or bits form the basis of the digital revolution. The familiar decimal or base 10 representation has been in use for over 1000 years, having been developed in India, improved by Arab mathematicians in the 12th century and brought to the West in the 13th century by the Italian mathematician Leonardo Pisano, better known as Fibonacci. Using decimal notation is natural for 10-fingered humans, but binary values work better when building machines that store and process information. Two-valued signals can readily be represented, stored and transmitted, for example, as the presence or absence of a hole in a punched card, as a high or low voltage on a wire, or as a magnetic domain oriented clockwise or counterclockwise. Representing information as bit patterns. The basic unit for representing discrete information in a computer is a bit. One bit can be considered as the information necessary for selecting one out of two possibilities. Each unique string of bits may be used to represent or code a symbol. Coding of character has been standardized to facilitate exchange of recorded data between computers. This module focuses on encoding text, numerical data and images. Each of these techniques is based on the fundamental concept of binary digits or bits. Number system. A number system or numeral system is a writing system for expressing numerals and a mathematical notation for representing numbers of a given set using symbols in a consistent manner. Number systems are basically of two types, positional and non-positional systems. In the non-positional number system, each symbol represents the same value regardless of its position in a number, and the symbols are simply added to find out the value of a particular number. In a positional number system, there are only a few symbols called digits, and these symbols represent different values depending on the position they occupy in the number. These number systems have a radix or base. The total number of digits available in the number system is defined as the base or radix of that number system. The value of a digit in a number is determined by three considerations: the digit itself, the position of the digit in the number, the base or radix of the number system. Decimal system. The decimal numeral system, also called base 10 or occasionally denary, has 10 as its base. It includes the digits from 0 through 9. The weighted value for each position is as follows: 10 raised to n, etc., 10 raised to 3, 10 raised to 2, 10 raised to 1, 10 raised to 0, point, 10 raised to minus 1, 10 raised to minus 2, etc., 10 raised to minus n. Each digit appearing to the left of decimal point represents a value between 0 and 9 times power of 10 represented by its position in the number. Digits appearing to the right of the decimal point represent a value between 0 and 9 times an increase in negative power of 10. For example, the value 735.185 is represented as follows: 7 into 10 raised to 2 plus 3 into 10 raised to 1 plus 5 into 10 raised to 0 plus 1 into 10 raised to minus 1 plus 8 into 10 raised to minus 2 plus 5 into 10 raised to minus 3, which is equal to 7 into 100 plus 3 into 10 plus 5 into 1 plus 1 into 0.1 plus 8 into 0.01 plus 5 into 0.001 equal to 700 plus 30 plus 5 plus 0.1 plus 0.08 plus 0.005, which is equal to 735.185. Binary number system. The base of the binary number system is 2. In this system, only two symbols 0 and 1 are used. Each position in the binary number system represents a power of 2. The weighted value for each position is as follows: 2 raised to n, etc., 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0, point, 2 raised to minus 1, 2 raised to minus 2, etc. 2 raised to minus n. All bits to the left of the binary point have weight that are positive powers of 2, and all the bits to the right of the binary point have weight that are negative powers of 2. The decimal equivalent of the binary number 110011.011 is 1 into 2 raised to 5 plus 1 into 2 raised to 4 plus 0 into 2 raised to 3 plus 0 into 2 raised to 2 plus 1 into 2 raised to 1 plus 1 into 2 raised to 0 plus 0 into 2 raised to minus 1 plus 1 into 2 raised to minus 2 plus 1 into 2 raised to minus 3, which is equal to 32 plus 16 plus 0 plus 0 plus 2 plus 1 plus 0 plus 1 by 4 plus 1 by 8, which is equal to 32 plus 16 plus 2 plus 1 plus 0.25 plus 0.125, which is equal to 51.375. The binary digit is often referred to by the abbreviation bit. A bit in computer terminology means either a 0 or a 1. Rather than accessing individual bits in memory, most computers use blocks of 8 bits or bytes as the smallest addressable unit of memory. A machine level program views memory as a very large array of bytes, referred to as virtual memory. Every byte of memory is identified by a unique number known as its address, and the set of all possible addresses is known as the virtual address space. As indicated by its name, this virtual address space is just a conceptual image presented to the machine level program. The actual implementation uses a combination of random access memory or RAM, disk storage, special hardware and operating system software to provide the program with what appears to be a monolithic byte array. Octal number system. The octal system has base 8. In this system, there are 8 symbols are used, such as 0, 1, 2, 3, 4, 5, 6 and 7. To the left of the octal point, all the bits have weights that are positive powers of 8, and all the bits to the right of the octal point have weights that are negative powers of 8. Thus, the column weights of an octal number are 8 raised to n, etc., 8 raised to 3, 8 raised to 2, 8 raised to 1, 8 raised to 0, point, 8 raised to minus 1, 8 raised to minus 2, 8 raised to minus 3, etc., 8 raised to minus n. Here, all bits to the left of the octal point have weight that are positive powers of 8, and all the bits to the right of the octal point have weight that are negative powers of 8, which is illustrated in the given example. The decimal equivalent of the octal number 4067.205 is 4 into 8 cube plus 0 into 8 square plus 6 into 8 raised to 1 plus 7 into 8 raised to 0 plus 2 into 8 raised to minus 1 plus 0 into 8 raised to minus 2 plus 5 into 8 raised to minus 3, which is equal to 2048 plus 0 plus 48 plus 7 plus 0.25 plus 0 plus 0.009765, which is equal to 2103.259765. Octal is sometimes used in computing instead of hexadecimal, perhaps most often in modern times in conjunction with file permissions under Unix systems. It is also used for digital displays. Octal numbers that are used in some programming languages like C, Perl, etc. for textual or graphical representations of byte strings. Hexadecimal system. In hexadecimal number system, the base is 16. Since the base is 16, we need 16 single character digits or symbols. The first 10 digits are the digits of the decimal number system 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. The remaining 6 digits are denoted by A, B, C, D, E and F, representing the decimal values 10, 11, 12, 13, 14 and 15 respectively. The largest single digit is F, which has a decimal equivalent of 15. Each position in a hexadecimal number system represents a power of the base 16. To the left of the hexadecimal point, each digit from the right to the left have the positional values 16 raised to 0, 16 raised to 1, 16 raised to 2, etc. And the right of the hexadecimal point, each digit from left to the right have the positional values 16 raised to minus 1, 16 raised to minus 2, 16 raised to minus 3, etc. Hence, the column weights of the hexadecimal number are 16 raised to n, etc., 16 cube, 16 square, 16 raised to 1, 16 raised to 0 point, 16 raised to minus 1, 16 raised to minus 2, 16 raised to minus 3, etc., 16 raised to minus n. The decimal equivalent of the hexadecimal number 13BF.5a is 1 into 16 cube plus 3 into 16 square plus b into 16 raised to 1 plus f into 16 raised to 0 plus 5 into 16 raised to minus 1 plus a into 16 raised to minus 2, which is equal to 4096 plus 768 plus 176 plus 15 plus 0.3125 plus 0.03906, which is equal to 5055.35156. Each hexadecimal digit represents 4 binary digits or bits called a nibble, and the primary use of hexadecimal notation is as a human-friendly representation of binary coded values in computing and digital electronics. For example, byte values can range from 0 to 255 in decimal, but may be more conveniently represented as 2 hexadecimal digits in the range 00 through FF. Hexadecimal is also commonly used to represent computer memory addresses. Generally, octal and hexadecimal number systems are used as a shortcut notation for binary. Conversion between number systems. Numbers expressed in decimal number system are much more meaningful to users than are values expressed in any other number system. Any number in one number system can be expressed in any other number system. There are certain methods to convert a number in a particular number system to any other number system. Computer codes. Not only numbers but letters and other symbols can also be represented using binary digits. Combinations of binary digits that represent numbers, letters or other symbols are called digital codes. There are different types of codes come into existence to represent numerical and alphanumerical characters. Representing text. In general, two-state devices are used as physical devices to store and process data in computers. The two states are on and off. Thus, all the data to be processed and stored in the form of text is normally represented in some code of two different symbols 0 and 1 to represent each state. Each of the different symbols in the text, like letters of the alphabet and punctuation marks, is assigned a unique bit pattern. Thus, the text is represented as a long string of bits in which the successive patterns represent the successive symbols in the original text. In the 1940s and 1950s, many such codes were designed and used but had severe communication problems. To alleviate this situation, the American National Standards Institute (ANSI) adopted the American Standard Code for Information Interchange or ASCII. This code uses bit patterns of length 7 to represent the upper and lowercase letters of the English alphabet, punctuation symbols, the digits 0 through 9 and a limited number of control information such as line feeds, carriage returns and tabs. Today, ASCII is often extended to an 8-bit per symbol format by adding a 0 at the most significant end of each of the 7-bit patterns. This technique not only produces a code in which each pattern fits conveniently into a typical byte-sized memory cell but also provides 128 additional bit patterns. Although ASCII has been the dominant code for many years, other more extensive codes capable of representing documents in a variety of languages are now competing for popularity. One of these, Unicode, was developed through the cooperation of several of the leading manufacturers of hardware and software. This code uses a unique pattern of 16 bits to represent each symbol. As a result, Unicode consists of 65,536 different bit patterns, which is enough to represent the text in Chinese, Japanese, Hebrew, etc. Standards for a code that could compete with the Unicode have been developed by the International Organization for Standardization. Using patterns of 32 bits, this encoding system has the potential of representing billions of different symbols. A file consisting of a long sequence of symbols encoded using ASCII or Unicode is often called a text file. It is important to distinguish between simple text files that are manipulated by utility programs called text editors and the more elaborate files produced by word processors. Both consist of textual material. However, a text file contains only a character by character encoding of the text, whereas a file produced by a word processor contains numerous proprietary codes representing changes in fonts, alignment, information, etc. Moreover, word processors may even use proprietary codes rather than a standard such as ASCII or Unicode for representing the text itself. Representing numerical values. Storing information in terms of encoded character is inefficient when the information being recorded is purely numeric. For example, the value 45 is stored as encoded symbols in ASCII using 1 byte per symbol, thus a total of 16 bits. Moreover, the largest number we could store using 16 bits is 99. However, by using binary notation, that is 0 and 1, we can store any integer in the range from 0 to 65,535 in these 16 bits. Thus, binary notation is used extensively for encoded numeric data for computer storage. Consider the following sequence: 0000, 0001, 0010, 0011, 0100, 0101, 0110, 0111, 1000. This sequence consists of the binary representations of the integers 0 through 8. By extending this counting technique, we could discover that the bit pattern consisting of 16 ones represents the value 65,535, which confirms that any integer in the range from 0 to 65,535 can be encoded using 16 bits. Due to this efficiency, it is common to store numeric information in a form of binary notation rather than encoded symbols. A system called 2's complement notation is common for storing whole numbers because it provides a convenient method for representing negative numbers as well as positive. For representing numbers with fractional parts such as 4.5 or 3/4, another technique called floating point notation is used. 2's complement notation. The 2's complement of a binary number is obtained by adding 1 to the 1's complement. The 1's complement is found by simply changing all 1's to 0's and all 0's to 1's. For example, the 1's complement of the binary number 110110111 is 001 001 00. Thus, the 2's complement is obtained by adding 1 to this number. 11011011 is the binary number. The 1's complement is 001 001 00, that is 001 001 00 plus 1, which is equal to 001 001 01. So, the 2's complement is 001 001 01. An alternative method of obtaining the 2's complement is demonstrated for the binary number 1101111. First, start at the right and write the bits as they are up to and including the first one. Next, take the 1's complement of the remaining bits. representing floating point values. In contrast to the storage of integers, the storage of a value with a fractional part requires that we store not only the pattern of zeros and ones representing its binary representation, but also the position of the radix point. A popular way of doing this is based on scientific notation and is called floating point notation. The following example explains floating point notation using only 1 byte of storage. Although machines normally use much longer patterns, this 8-bit format is representative of actual systems and serves to demonstrate the important concepts. First, designate the high order bit of the byte as the sign bit. A 0 in the side bit means that the value stored is non-negative, and a 1 means that the value is negative. Next, divide the remaining 7 bits of the byte into two groups or fields, the exponent field and the mantissa field. Let us designate the 3 bits following the sign bit as the exponent field and the remaining 4 bits as the mantissa field. Suppose a byte consists of the bit pattern 0, 1, 1, 0, 1, 1, 1, 1. Analyzing this pattern with the preceding format, we see that the sign bit is 0, the exponent is 1, 1, 0 and the mantissa is 1, 0, 1, 1. To decode the byte, we first extract the mantissa and place the radix point on its left side, obtaining 1, 1, 1, 1. Next, we extract the contents of the exponent field 1, 1, 0 and interpret it as an integer stored using the 3-bit excess method. Thus, the pattern in the exponent field in our example represents a positive 2. This tells us to move the radix in our solution to the right by 2 bits. A negative exponent would mean to move the radix to the left. Consequently, we obtain 11.11, which is the binary representation for 33. Here, the sign bit is 0. The value represented is thus non-negative, represents 33 by 1. If the pattern is 1, 1, 1, 0, 1, 1, 1, 1, the same as before except for the sign bit, the value represented would be minus 33 by 1. Representing images. For an image to be processed in a computer, it must be represented in a specific form which is understood by the computer. Today's computer applications involve not only the text and numeric data but also some complex processing. They include images, audio and video. Important techniques for representing images can be classified into two categories: bitmap techniques and vector techniques. In the case of bitmap techniques, an image is represented as a collection of dots, each of which is called a pixel, that is picture element. A black and white image is then encoded as a long string of bits representing the rows of pixels in the image, where each bit is either 1 or 0 depending on whether the corresponding pixel is black or white. This is the approach used by most facsimile machines. This bitmap approach is generalized further for color images, where each pixel is represented by a combination of bits indicating the appearance of that pixel. Two approaches are common. In one called RGB encoding, each pixel is represented as 3 color components: a red component, a green component and a blue component corresponding to the 3 primary colors of light. 1 byte is normally used to represent the intensity of each color component. In turn, 3 bytes of storage are required to represent a single pixel in the original image. A popular alternative to simple RGB encoding is to use a brightness component and 2 color components. In this case, the brightness component, which is called the pixel's luminance, is essentially the sum of their red, green and blue components. Together, these 3 components contain the information required to produce the pixel. One disadvantage of bitmap techniques is that an image cannot be rescaled easily to any arbitrary size. Essentially, the only way to enlarge the image is to make the pixels bigger, which leads to a grainy appearance. Vector techniques provide a means of overcoming this scaling problem. Using this technique, an image is represented as a collection of lines and curves. Such a description leaves the details of how the lines and curves are drawn to the device that ultimately produce the image, rather than insisting that the device reproduce a particular pixel pattern. The various fonts available in today's word processing systems are usually encoded using vector techniques in order to provide flexibility in character size, resulting in scalable fonts. Vector representation techniques are also popular in computer-aided design or CAD systems, in which drawings of three-dimensional objects are displayed and manipulated on computer screens. Communication errors. Digital circuits are normally designed with extreme accuracy such that the probability of occurring even a single error is very small. But when information is transferred back and forth among the various parts of a computer or in storage, a chance exists that the bit pattern ultimately retrieved may not be identical to the original one. Particles of dirt on a magnetic recording surface or a malfunctioning circuit may cause data to be incorrectly recorded or read. And in the case of some technologies, normal background radiation can alter patterns stored in a machine's main memory. The errors take the form of undesired changes in the bits that make up the coded information. That is, a 1 can change to a 0 or a 0 to 1. To resolve such problems, a variety of encoding techniques have been developed to allow the detection and even the correction of errors. Today, because these techniques are largely built into the internal components of a computer system, they are not apparent to the personnel using the machine. Nonetheless, their presence is important and represents a significant contribution to scientific research. The types of codes which only detects errors are known as error detecting codes. The types of codes which can both detect and correct errors are known as error correcting codes. Error detection scheme. Error detection is most commonly realized using a suitable hash function or checksum algorithm. A hash function adds a fixed length tag to a message, which enables receivers to verify the delivered message by recomputing the tag and comparing it with the one provided. There exists a vast variety of different hash function designs. However, some of them are widely used because of either their simplicity or their suitability for detecting certain kinds of errors. Repetition codes. Repetition code is a coding scheme that repeats the bits across a channel to achieve error-free communication. Given a stream of data to be transmitted, the data is divided into blocks of bits. Each block is transmitted some predetermined number of times. For example, to send the bit pattern 1001, the 4-bit block can be repeated 4 times, thus producing 1001, 1001, 1001, 1001. However, if this 16-bit pattern was received as 1010, 1001, 1001, 1001, where the first block is unlike the other two, it can be determined that an error has occurred. Repetition codes are not very efficient and can be susceptible to problems if the error occur in exactly the same places for each group. Example, 1010, 1010, 1010, 1010 in the previous example would be detected as correct. The advantage of repetition code is that they are extremely simple. Parity bits. A parity bit is a bit that is added to ensure that the number of bits with value of 1 is a given set of bits in always even or odd. Parity bits are used as the simplest error detecting code. For binary digits, there are two types of parity bits, even parity bit and odd parity bit. An even parity bit is set to 1 if the number of ones in the given set of bits is odd, thus making the total number of ones even. An odd parity bit is set to 1 if the number of ones in the given set of bits is even, making the total number of ones odd. Example, transmission using even parity. If the stream of data to be transmitted is 1001, the parity bit value is calculated by XORing the bits, that is the parity bit value equal to, so add the parity bit 0 and sends 10010. At the receiving end, if it receives 10010, computes the parity and gets reporting correct transmission. This mechanism enables the detection of odd number of bit errors. If an even number of bits have errors, the parity bit records the correct number of ones, even though the data is corrupt. That is, for the above sequence, if the data received is 10100, the parity bit computed will be 0 and reports correct transmission, but the data is not the same. Before we conclude, please try to answer these questions. How the data is stored in a computer? Define number system. What is the importance of binary system in the curriculum of computers? What is meant by computer codes? What are the different types of data processed by a computer? Explain the methods for representing text in computers. Explain the methods of representing numerals in binary form. How can an image be represented in digital form?